The collapse of a steel beam under pressure is the macroscopic manifestation of microscopic geometric laws executing at the atomic scale. A material's macroscopic stress-strain behavior and work hardening rate are deterministically controlled by its internal crystallographic slip capabilities. To understand these mechanisms, we must analyze the three foundational crystal structures used in industrial metals: face-centered cubic, hexagonal close-packed, and body-centered cubic. Predictable engineering manipulation of these metals depends on the specific structural anisotropies within each atomic lattice. Plastic deformation generally relies on slip, a process where dislocations glide along close-packed planes in close-packed directions. This diagram identifies the geometric constraints for the face-centered cubic, or FCC lattice. Here, slip occurs on 111 planes along 110 directions. Because the FCC lattice contains 4 such planes, each with 3 directions, the structure possesses exactly 12 primary slip systems. To initiate this glide, the dislocation must have a perfect Burger's vector, with a magnitude and direction indicated in the red box. While these 12 systems provide FCC metals with high baseline ductility, this count alone does not explain how these metals actually work hardened under stress. In an FCC lattice, perfect dislocations are energetically unstable and tend to spontaneously dissociate. This central inequality represents Franck's rule, which states that a dislocation's elastic strain energy is proportional to the square of its Burger's vector. To reach a lower energy state, the lower right diagram shows a perfect dislocation mathematically and physically splitting into 2 Shockley partial dislocations. This energetic requirement to split changes the physical shape of the dislocation, creating a sequence of effects that dictate the material's mechanical properties. Looking at the right side graphic, we can see the result of this split. The region between the 2 partial dislocations creates a stacking fault in the atomic lattice. In this faulted region, the standard FCC stacking order changes locally to mimic an HCP crystal structure. Creating this region requires a specific amount of surface energy per unit area, known as stacking fault energy, or SFE. The exact relationship is defined by the formula in the theorem box. This formula balances the elastic repulsion of the partials against the surface tension of the fault. Note that the separation distance, d, is inversely proportional to the SFE of the material. This width becomes a primary factor in the dislocation's ability to move and interact during subsequent deformation. Once a dislocation is extended with a stacking fault, it is rigidly confined to its primary slip plane. To switch planes and bypass obstacles, dislocations must use cross-slip, a mechanism illustrated here in stages 1 through 5. Cross-slip has a strict physical prerequisite. As shown in stage 2, the extended partials must first be forced to recombine into a perfect dislocation at a constriction point. This flowchart connects SFE to the material's hardening behavior. A wide stacking fault, typical of a low SFE material, requires immense energy to constrict, which suppresses cross-slip. Looking at the data table, we see this in practice. Stainless steel's low SFE prevents cross-slip and causes rapid hardening, while aluminum's high SFE allows for easy cross-slip and a lower hardening rate. While some dislocations can glide, others are sessile, meaning they are incapable of movement on a slip plane. This atomic grid illustrates a Franck partial dislocation. Here, the insertion or removal of a 111 plane creates a Burger's vector perpendicular to the close-packed plane. Because this vector points away from the glide path, these structures are trapped and can only move via non-conservative climb. During severe deformation, multiple slip systems are active simultaneously. This graphic shows what happens when 2 separate 111 slip planes intersect. At the intersection line, partial dislocations from both planes combine to form a Lomer-Cottrell barrier, or stair rod dislocation. These locks act as stable barriers that impede dislocation motion. As subsequent dislocations pile up against these obstacles, the material's resistance to further deformation increases, providing a primary microstructural driver for work hardening. Hexagonal close-packed, or HCP structures, offer a stark contrast to the multi-system mobility seen in FCC. This hexagonal model highlights HCP's restrictive nature. Slip is generally limited to just 3 basal systems, unless the material is subjected to high stress or temperature. Transitioning to body-centered cubic, or BCC structures, reveals a lattice with no true close-packed planes. This summation shows how BCC compensates for that lack of close packing. It can activate up to 48 different slip systems across various planes. This high system count enables pencil glide. As shown in Diagram D, screw dislocations in BCC are not confined to a single plane and can move in wavy, three-dimensional paths. This unconstrained slip allows for extreme malleability, fundamentally separating BCC's deformation behavior from the rigid limitations of HCP and FCC. This comparison table demonstrates material deformation is a strict execution of atomic-level geometrical rules. The FCC row identifies a structure with high slip capability, heavily regulated by SFE and immobile locks. These rows contrast HCP's brittle anisotropy against BCC's massive 48-system mobility. Ultimately, the macroscopic engineering reality of metal forming and structural failure relies on exploiting these exact microscopic crystallographic constraints.